All right, so now we're going to take a look at finding the volume of a cone. So kind of where does that formula come from? There's a bunch of videos online where you can see somebody taking a cone that has the same height and radius as a cylinder, and they'll show you filling up the cone with water and dumping it into the cylinder, and they'll show you that it fills it up in exactly 3 tries, right? Which means that the volume of a cone is actually just 1/3 that of a cylinder, which is great, but why does that work? So let's take a look at this here. So here we're going to do some calculus, some integration, without actually getting into the calculus side of it. Okay, so here we're going to take a look at a cone. So we've got the cone on the left-hand side, and we look at it from the side view. It looks like an isosceles triangle on the right. Okay. Now, the idea that we're looking at here is what happens if we are to go ahead and instead of taking a look at this shape as is, we go ahead, or in terms of finding volume as is, we try to approximate the volume by putting in, like stacking 2 cylinders on top of each other. Of one of them where it's going to end up being, where they're both going to have the same height. In this case, the height of the cylinder, the triangle, the cone, sorry, is h, which means that the height of each of the cylinders is going to be h over 2. Okay. Now, what we're trying to do here is we want to go through and stack these cylinders and create cylinders that are in a way that they will intersect the midpoints, or I guess the quarter points of the sides of this triangle, right? So I get intersecting here, 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 and then up at the top there, right? So it creates these kind of steps here, okay? And so what we can do is we can think about this if we divide it as it drew these little vertical dashed lines here. We can break this up into 4 real pieces here. 1, 2, 3, 4, and those are going to be congruent to each other, okay? Which means that if the radius is the full distance across here, where r is, that means that we're 3/4 of it, right? So we're 1, 2, and then 3 of those. That means that the radius of the bottom cylinder is going to be 3 over 4 r. All right, so 3/4 r. The one up at the top only fills up one of those lines there, so it's going to be 1/4 r. Now, keep in mind this is a side view of a cylinder. If you look at a cylinder from the side, it looks like a rectangle. So trying to simplify it and taking the 3-dimensional element out of it and just looking at it as is. Okay? So in this case, though, we're going to take a look at an expression for the volumes of those cylinders. So if I'm taking a look at the volume of the big cylinder, it's going to be pi, instead of r, it's 3/4 r, because that's the radius of it, squared. And instead of the height just being h, it is h over 2, as we did in the diagram up above there. And the volume of the small cylinder is going to be pi, and then instead of r, it's 1/4 r squared, and then the height is, once again, h over 2. Okay. So the volume of this thing, the total volume that is going to be the sum of those two things. Volume of the big plus volume of the small. Now, those are cylinders, that is. So this is going to be pi, and then 3 over 4r, that quantity squared. If I distribute that square, it becomes 3 squared over 4 squared, which is just 9 over 16, and then r raised to the second is r squared. Right? And then times h over 2. Plus, and I do the same thing over here. I have pi, and 1/4 squared is going to be 1 over 16. And then r squared is just r squared. Right? And then I have h over 2. Okay. So now if I actually multiply within those individual terms here, 9 over 16 times that 2 in the denominator becomes 9 over 32. And there's still the pi, the r squared, and the h is now just on its own. Do the same thing over here, and I end up with 1 over 16, or sorry, 1 over 32, because it's the 16 times 2, pi, and then I have r squared h. Right? Those are like terms, right? The like terms, they have the same variables raised to the same powers. In this case, it's a pi r squared h, right? So really, I could write this in the end as 9 plus 32, sorry, 9 plus 1, which is 10 over 32, pi r squared h. Now, if we take a look at our calculator and we do 10 over 32, we see that 10 divided by 32 comes out to be exactly 0.3125, which is getting close to 1/3, because 1/3 is 0.3 repeating. Right? So if we continue this process, and instead of taking a look at with 2 cylinders here, we did with 3 of those cylinders, calling them discs here, we would end up with the coefficient being 35 over 108. And 35 divided by 108 comes out to be, 35 divided by 108 is approximately 32.4. Actually, 0.324. which is almost that 0.33. So if we were to continue to do this and add in more and more of those cylinders there, it'll get closer and closer to approximating the volume. Okay? And this is where the idea of calculus comes in. We're trying to find the area underneath the curve, which is integration, the second half of calculus. And so in this case right here, as we're taking a look at it, we can see that as the number of cylinders gets to be an infinitely large number, what's going to happen is that that coefficient is going to get infinitely close to being 1/3. So what we can say that here is that we can conclude that the volume of a cone is going to end up being 1/3 pi r squared h, which is the same thing that we've talked about in the beginning. Okay? And this extends very nicely because pyramids share a similar idea here with that formula, except the volume of any pyramid is just going to be 1/3 the area of the base, which is pi r squared when we're talking about a cylinder, times the height. So it's just 1/3 of the area of a prism that has the same base. Cool stuff. All right, hope it works for you.